So I guess the story is like the walk-ins and it was there something.
Great, so let's go ahead and get started. We may have some others trickle in. Thanks for taking the time to attend. We'll be talking primarily about our work developing tools for doing high-performance ethylene oxide detection. We'll cover some of the other applications or tools that have been used for as well in the context of this conference, particularly BTEX analysis, et cetera. We'll quickly review the state of ethylene oxide monitoring. We won't go into too much detail. You've probably heard a number of talks here today. We'll talk about the underlying technology that our platform uses to do general chemical analysis. We'll talk specifically about some of the challenges and work that's been done to enable high performance analysis for ethylene oxide. It's a little bit harder than a number of other compounds to get high stability, high accuracy, part per trillion detection for this compound. And then we'll talk through some of the performance, the way our analyzer gets used in the field, how do you translate lab quality data to doing those type of measurements outside of the laboratory environment. And then we'll talk a little bit more broadly about the different types of ways that our tool gets used for doing monitoring. Ethylene oxide is a new compound, so we don't have as deep a data set yet on field work of ethylene oxide, but we've got extensive field work looking at other classes of compounds. About our company, so we're a company that came out of Caltech and Stanford, originally working on using tangible resources for metrology applications, which is where our name came from. It has nothing to do with red tape. But we've been developing, we took the tools that were originally used for these quantum resources and we realized we can apply them to doing high performance analysis. So very high performance optical analysis using the signal processing techniques that came out of quantum state estimation to improve the signal to noise of our instrument, and then to translate that into some of the back trajectory estimation techniques, our modifications of the tools, the maximum likelihood tools developed in those scenarios. We'll be talking primarily about our AROMA platform, which stands for Autonomous Rugged Optical Multigas Analyzer, but of course that was made up entirely to fit the acronym. But our goal is to deliver best-in-class trace gas and vapor analysis, really laboratory-grade data, and we'll talk a little bit later about the validation behind that. But really, our goal is to provide data that can be used with laboratory quality assurance, multiple line of evidence, confirmatory analysis, to allow real-time decision making without worrying if false positive or false negative. As you heard in the last talk, QA/QC is critical. So we focus on developing a tool which is not giving you a number based on a single measurement. It is a suite of validated measurements, and we'll show the performance that we've been able to achieve against regulatory instrumentation a little bit later. Our first product to market was the AROMA, and that was first deployed, actually the prototype was first deployed in 2017. So it's a fairly new technology platform, which has been rapidly growing in adoption. So ethylene oxide, it's a compound which is used critically in the chemical sterilization industry. It's also a common chemical precursor. It's used in a number of processes. I mean, it's actually kind of magic. I mean, we visited some of the sterilization facilities. You get a pallet in, you just put the pallet, you put it in your humidifier chamber, you put it in your sterilization chamber, you flood it, and you have products. You never open the boxes. They come out the other side and they're sterilized, ready to go. So it's a critical part of our medical supply chain infrastructure. Not surprisingly, I mean, this chemical kills things very effectively. It's a very good sterilization compound. Reassessment of the toxicology has lowered the threshold significantly. It's now potentially down single-digit parts per trillion for the 1 in a million cancers. And so it's very much changed the regulatory structure recently in terms of what you need to look for ethylene oxide. It's a pretty reactive chemical. It's pretty nasty. It polymerizes. It in fact will polymerize explosively in the wrong environments. It'll polymerize inside of your TO15 canisters. There are a number of challenges to get accurate, particularly low-level ethylene oxide analysis. And on top of that, there are not currently good techniques to get low detection limits, or below 50 parts per trillion or so has been challenging even for TO15, TO15A methodology, which means we don't really understand what ethylene oxide looks like in the world today. So, maybe you're just going to see concentrations of ethylene oxide at, like you see benzene. There's benzene everywhere, or maybe ethylene oxide everywhere, and more data is starting to show there is a stable ethylene oxide background. And so in order to regulate effectively, you need to understand what these backgrounds are, and then we need to be able to resolve anthropogenic differences above and beyond those background concentrations. And of course, if you want to be able to do anything interesting with the data, your limits of detection need to be much better than the limits that you're looking at. If you want to be able to do back trajectory analysis, any noise you have when you put into the source models blows up your source estimation abilities. And so really, if you want to be doing back trajectory, make sure that the limits of detection for your tools are below, significantly below the action levels. If you don't have that, you can't do good back trajectory estimation. A number of techniques are coming online now. It's a little early to really say how all these techniques are going to pan out. FTIR, we've heard a lot about FTIR. It's one approach which is currently deployed for ethylene oxide analysis. PTR top with either TC on the front end or reagent chemistry is looking like it may deliver reasonable results for ethylene oxide. GCMS, of course, your sort of gold standard. Cavity ring spectroscopy, and then our tool, which is a GC or thermal desorption cavity ring spectrometer. And so, again, this is a list growing. Everyone's interested in this right now. It's sort of the compound stories. Let's see how as I mentioned before, our goal is really to deliver an analytical experience where you don't need to have an expert operator. You're not spending your time validating the data. You're not doing sensitive data review. You want multiple lines of evidence so that when you see a compound and you may need to evacuate based on these concentrations, you want to be able to make decisions where you have a very good grounding. You understand exactly what the signals are. There are no false positives. There are no false negatives. We do this, and I'll explain it a little more mechanically later, but we have multiple lines of evidence. We're using multiple lines to demonstrate that we are seeing the compounds we think we are. It needs to be able to operate in industrial, robust conditions. It needs to be able to operate in, potentially, if you're doing stack emissions testing, saturated humidity at 150 Fahrenheit, so very harsh conditions. You need reliable data quality, and it's something that it's going to actually be used. You can't have a lot of consumables. It can't be using kilowatts of power. But at the end of the day, I think what's really critical is that you deliver laboratory quality results. So it's data that can be trusted, that can be validated against any gold standard methodology and stack up. Our tool has two modes of operation, and I'll describe these a little bit more. We have an analysis lab scan mode, and this is a part per trillion limited detection analysis mode where we do GC light separation on the front end. We put that into a broadband cavity ring spectrometer where we measure a number of spectral points simultaneously, and it will actually in very rapid succession. So we get data that looks very much like GCMS. You have spectroscopy axis, you have an arrival time axis, and this lets you operate in very dense environments to be able to distinguish specific compounds, even in very complex matrices that are reflective of the real operating conditions. And this analysis takes 15 minutes. We also have a rapid scan mode where we actually skip that front end. We do direct spectroscopy. Our tool has some real advantages where it's able to do broadband spectroscopy. So our standard tool, the ethylene oxide tool, standard tool covers about 150 nanometers in the near infrared. We have extended tools that include things like sulfide, carbon monoxide, cyanide, et cetera, which will span more than 250 nanometers in the near infrared, and we can hit essentially an arbitrary wavelength in that region in a small fraction of a second. So we get very high performance CRDS over a broad spectrum, which allows us to do small molecule identification. So ethylene oxide, methane, CO2 come out as speciated numbers in that rapid scan mode. But we also, because we understand our foregrounds very well, so we're measuring these small molecules, we can also use additional wavelengths, almost like PID channels. So we can have a wavelength which targets aromatics. It is primarily responsive to aromatics. We can have a wavelength which targets alkanes, for example. So you can pull out your ethylene oxide concentrations, but you can also say, well, I'm also seeing a diene signature in this. I'm seeing an alkane signature in my background, so I might know where to look in my process stream to identify what that source was. Yeah, and this is a few seconds. You're getting part per billion sensitivity in this mode. Better detection with the PIDs, very good stability, all the advantages of CRDS, but then the ability to switch over and do this extremely high performance part per trillion detection analysis on the back end. To describe a little bit more what the system is doing, so we have sort of two critical subsystems. The first is our inlet separation front end. So we grab an aliquot of atmosphere onto a sorbent material. And this is used only in the analysis. That's bypassed when we're doing our rapid scan direct CRDS. So In our analysis mode, we're pulling in, we're grabbing an aliquot sample, variable sample volume, easily programmed by the user, so you can go from parts per trillion limits detection, one measurement, up to tens or hundreds of parts per million on the next cycle, just by reprogramming what your sample volume is. We collect on that, and then instead of just doing flash desorption, we do a process of ramped thermal desorption. So we then get chemical separation, and of course, there's more subtlety involved in what's actually being done here to get effective separation from these molecules. That's the broad idea. We take the output of that system and we put it into our broadly tunable CRDS core. So now we're able to take spectroscopy on that to identify the different molecules, to resolve backgrounds. And the nice thing about spectroscopy is you can make yourself blind to compounds you're not interested in. So in a different application space, but in a petrochemical in-field process fluid analysis, we were able to beat GCMS by a factor of 50 sensitivity, not because our instrument is fundamentally more sensitive, but because we could completely eliminate hydrocarbons from our analysis by choosing spectra effectively. So there are some real advantages to using spectroscopy, given the broad linearity of these techniques. And using a technique we had developed in the quantum optics space, we had extraordinarily high sensitivity from our CRDS engine. So our minimum detectable absorbance length is 1.2 10 to the minus 12 inverse centimeters per root hertz. To give you context, this is a material that's so transparent, it's 10 times the distance to the moon, you lose half the length. So yeah, you're looking at path lengths of a kilometer. If you're doing open path, these CRDS systems, your effective path length in our system is 40 kilometers. But because of the way you do these measurements, you're able to get extremely good fidelity. Just as a very quick primer, I'm not going to go into much detail. Cavity ring spectroscopy is an excellent technique for overcoming technical noise in optical systems. The way that it works is you have two or more highly reflective mirrors. You excite those mirrors with a light source, a laser in most cases for cavity ring spectroscopy. And then instead of just measuring how much light comes through that system, you actually turn your laser off. You now measure the decay in it. So it's really like you strike a bell, and instead of measuring how loud is the bell, you say how long does it take to decay. The advantage of this is that you lose a number of technical noise sources you're measuring in time domain, and you can measure that decay envelope to a part in 10 to the 4 or a part in 10 to the 5. So you have a 40-kilometer path length. You're sensitive to changes in absorption at the part of 10 to the 4 or 10 to the 5 on each measurement, and you then measure that in our case about 10,000 times a second. So you get extraordinarily good data fidelity. So this means your back-end detector is incredibly sensitive, and you can use that sensitivity and dynamic range to now improve the overall measurement performance of your system. Spectroscopy, so you tend to see CRDS used for small molecules. These are molecules like what you see in the top left. So this is the methane spectrum, the near infrared. The molecules are simple, and they have resolved low vibrational modes. So each of these spikes corresponds to a single vibrational transition, where you're looking at these different rotational modes corresponding to each spike. But as the molecule gets bigger, the density of states increases, and you kind of think of it as like your fingers on your hand, right? You just start to get closer and closer, and so for big molecules, you don't have these resolved spikes, you have these broad spectral features. So it's a challenge in optical systems, particularly in the near infrared, to be able to do positive identification of molecules, because you have these broad spectra that are very similar. And you look at this and you think, oh, I can pull out benzene, for example, and have it kind of shifted over. But the problem is, you need to be able to measure that benzene concentration reliably when you're looking at concentrations of, say, toluene that are 1,000 times higher. So you need to be able to do this reliably in these very dense matrices. And that's where the separation technique is critical. So any of these techniques where you're doing direct optical spectroscopy, it's not that difficult to saturate your system. So if you can do some separation, now you can pull these molecules apart and do the positive identification in essentially arbitrarily complex molecular environment. So what does the data actually look like that comes out of the instrument? So what we do is now we're measuring, our measurement's happening here on the x-axis. The different colors correspond to the different wavelengths. It looks like soup, like the raw data coming out of the analyzer looks kind of like soup, but the magic happens when you essentially divide everything by what the optical spectrum is. And what was kind of a mess of different wavelengths all of a sudden collapses down, and you're able to very clearly identify the different molecules and species. So, looking at, say, this is trichloroethylene, right, which essentially overlaps with benzene. TCE wavelengths are independent of benzene, and you can pull it out completely independently. So here we say, okay, we have good spectral agreement, and we also have correct arrival time. And so we know that that is TCE, and guaranteed 100% confidence that is TCE. We have spectral match, we have the arrival time match. It's as good as you get out of TDCMS in terms of your data validation. Ethylene oxide, I'll sort of specialize now to our ethylene oxide work. I'll start with some of the spectroscopy, then we'll talk about the sampling challenges. There are things that make ethylene oxide hard. So first of all, ethylene oxide kind of lives in the gray area between those two types of molecules that I described earlier. Pretty small molecule. It actually has a couple of resolved spectral features at like 1690 nanometers and 1643 nanometers, but it doesn't have that richness of structure that you have for small molecules like methane and water, for example. But there are these sharp resolved spectral features, and these features are sharp enough that compared to any large molecule background, the large molecule background varies slowly over those specific features. But as you can see when you zoom in, it's actually quite broad in comparison to the backgrounds. And if you actually look at the intensity of the spectrum, if you're looking at, say, a part per billion of ethylene oxide, you're actually swamped by your ambient concentrations of methane and water in this case. So if you want to be able to reliably spectroscopically measure ethylene oxide in the near infrared, where there's fantastic technology in the near infrared optically, you have to know all of your backgrounds extremely. You have to have very high confidence. And this is a place where our broadband CRDS has been critical. So we can pick the optimal wavelengths in this range to measure water. We can pick the optimal wavelengths to measure CO2. We can pick the optimal wavelengths to measure methane. And so we can have part in 10 to the 4 accurate measurements of those backgrounds and then specialize on looking at ethylene oxide, and we can accurately and reliably remove those backgrounds from our equation and do positive identification here using the spectral information of ethylene oxide alone. So this is the measurement that we do in the rapid scan mode of our instrument, and we use the same spectroscopy in the analysis mode to be able to isolate and positively identify the ethylene oxide compound. So as I mentioned before, our front end, we're getting very little into detection. We are doing a sample volume collection, so we'll grab our BTEC analyzers. We'll grab from a milliliter up to 5 to 10 liters before we reach breakthrough volume. And ethylene oxide turns out to be a lot more challenging. So what we've done, and I'll briefly describe some of this just to give people a sense of what ethylene oxide looks like. These same challenges are going to come up if you're trying to do passive sampling of ethylene oxide. And of course, on top of that, you're also looking at polymerization, long-term stability, et cetera, which can be issues with passive sampling. But your goal is to be able to accurately recover the mass of ethylene oxide that's delivered onto the system in arbitrary conditions. And this is really critical. I mean, it's very easy to do lab results, which are great, and then get out to the real world and not get good reliability. So in our analyzer, we found that through special selection of absorbents, special selection of operating temperatures, recovery, absorption temperatures, et cetera, it's possible to get very good recovery up to fractions of a liter. And that's sufficient to get these very low levels of detection. So there's no need to push the technology beyond that. But ethylene oxide, you do your first measurements on ethylene oxide, you run it in zero air, and you get this beautiful recovery curve of 2 liters, and nobody really cares to go past that. It's a huge volume. And then you're like, well, what's the first nasty thing I can do, right? Okay, I start putting in a little humidity. And the thing is, ethylene oxide looks a lot like water. And it immediately starts competing with the water. And so you very quickly start losing the ability to recover ethylene oxide and essentially saturating your sorbent material. This is something, this is the current system we're using. Our initial, our first test. Yeah, we know what we're doing, we're great. Yeah, we got, I think we only got 0.1, 10, 100 milliliters of sampling before we started to see this rollover behavior. And so there is real room for optimization, optimizing sorbent materials, optimizing the various chemical parameters in your system. You also have issues with ethylene oxide. If you use a standard DSOR ramp for standard DSOR temperatures on ethylene oxide, pretty sure it's polymerization that's triggered. But as you increase your temperature, you see your recovery start to drop pretty drastically. And so there are, again, in a sorbent-dependent way, there are optimal parameters for your recovery so that you don't have any unwanted chemical processes destroying ethylene oxide on your sorbent. We've never seen this with other compounds unless going to very high temperatures where you can crack them. Again, ethylene oxide has been a little more of a challenge. So looking now at the lab scan mode. So in the lab scan mode now, we are looking at this evolution-like behavior. So to give you a sense for why we're sort of talking part per trillion limits of detection, Again, we're looking at spectral information. We primarily highlighted the two wavelengths, which are on and adjacent off peak for ethylene oxide for this. I mean, this is data, I guess, this is zero-rate data to give you a sense of what the signal to noise in these analyzers look like. This is a 50 part per trillion signal. So this is really what the limit of detection is for almost all standard ethylene oxide analysis tools. And there's no noise, right? You can see no noise on the signal in our system. Going down now to a 2 part per trillion signal, it looks pretty flat on this scale. But if we actually zoom in now on the signal, right, again, there is some scattering here, but you're averaging over the points in each of these spectral clusters. You're getting very good fidelity at 2 parts per trillion. Now you're seeing still very high above the signal to noise of the instrument. Honestly, we have limitations on our current CAL systems, and to get down really any lower than this. But based on decay, looking at the decay envelopes, we actually think we can hit high hundreds of parts per quadrillion method detection limits for these compounds. But again, very robust detection. So quantitation limits aggressively at 10 parts per trillion. So that's well above your signal noise. That's above your MDLs are down again. 2 parts per trillion is clearly above the MDL of this instrument. Again, now this is just showing the lab scan. It's CRDF, so it's a nice accurate technique. You can see a little of the clear down in your system as you transition between different concentrations. CRDS is great. Use direct modes. You're doing very fast direct sampling with the analyzer. So yeah, the CRDS is that gives great response. What does this look like now in the real world? So there are a lot of questions about what do ethylene oxide backgrounds actually look like. So this is data which was collected at our facility in Central California. Again, so showing backgrounds that are ranging from about 20 parts per trillion, up to 50 or 60 parts per trillion. You can get a sense, right? Is this actually a stable analysis, right? So this is now real ambient sampling, so you do expect there to be variations, but you can see very tight clusters of data points, very low noise, which indicate this is kind of an upper bound worst case of what the noise floor of the analyzer actually is in these scenarios. Very tight data, and you do see, yes, there is clearly ethylene oxide background concentrations. I mean, we're just in an industrial park, not far from San Francisco Airport. And again, there's ethylene oxide in that environment, which are certainly above the 1 in a million cancer risk, and there's no local source of ethylene oxide. Unless our facility, which was actually a medical device facility before we moved in, stashed the ethylene oxide in there. I don't think they did. It's actually higher outdoor than it's indoor. But it's again, there is biotech. We're not far from Genentech, for example, so it wouldn't be a shock if you do have some background levels. Analytical performance. This is kind of showing the different types of compounds. So in this ethylene oxide rapid scan, we pull a lot of the light molecules as well. A lot of the alcohols come out. Ethylene oxide and below 10 parts per trillion. Benzene, you're also getting your sort of full performance for benzene. A number of the other high toxicity small light molecules are also analyzed in this mode. And we're sort of primarily interested in the ethylene oxide in the context of this talk. Again, how can tools like this change the way that you're able to do business, right? So number one is the ability to do rapid response. Do you actually, you have an ethylene oxide release event? Is it a short-term acute concern to the community? Are there backgrounds that are problematic? So there are a number of known backgrounds, acetaldehyde, for example, which are known potential interference with a number of different detection methodologies. You don't want to be making shelter-in-place determinations between faulty data, where you're seeing other potential co-contaminants that are problematic. Other tools have difficulty with ethylene propylene, for example. None of those are issues with reduction. You can do hyperlocal mapping, you can do high-resolution mapping in rapid scan mode, or you can do slightly lower resolution, but still good resolution mapping in the lab scan mode. You can also do, of course, process control. You can detect leaks early. You can determine if you have breakthrough in your sorbent beds. You can do stack testing, et cetera. And then critically, you're also doing multi-compound analysis. So if you do see an elevated concentration, you can use that to facilitate isolating stages in your process, for example, that are correlated with the other compounds that are co-contaminants, and understand where those are coming out of your process stream. So performance and validation, I mean, I think this is really critical. I think this is where kind of if you want to believe a technology is going to be useful in the field. So this data, I will say, is not specifically for ethylene oxide. That's a brand new analyzer. We have one currently at Aurelie where they're doing, not just our instrument, a bunch of bench instruments undergoing bench validation. But we're expecting to see some of that performance coming out. We anticipate it's going to be similar in quality to this performance. I'll show this performance of the other compounds that just need method validation and backup on the underlying method, just the same as the ethylene oxide would. So, for example, we did a 30-day unattended side-by-side with the Bay Area Air Quality Management District. This was installed in their Livermore testing station where they have a dual column GCFID, which is doing hourly samples. It's calibrated nightly, or at least it undergoes QA/QC nightly. Showing just two of the analytes, benzene and toluene, and the agreement is as close to perfect as you can reasonably expect analytical instruments to be. This means both instruments are actually working really well. And so again, this data is true co-sampling. We downrated our sampling time to match their 35-minute interval starting 5 minutes after the hour. So it's true comparative sampling on a split inlet line. And again, there are no outliers in this data. It's essentially perfect for that regulatory dual column system. We've also done other types of work. So with GSI and ASTCP, did a fluorinated solvent study. This is a really nasty matrix. This is in live sanitary sewer head space. Undergoing significant variations in industrial areas. So there's a lot going on in these spaces. Again, 99.95 R squared against a field GCMS instrument. And then with region 9 EPA, this is TO15. Sorry, this ended up shrinking really badly. This is TO15. It's a little bit less of a tight agreement. It's only R squared of 0.98. This is soil vapor analysis where we're doing sequential sampling. So they would grab a TO15 canister, send it off to the region 9 lab, and then we would do our analysis. And there's about 60 points in here. And again, so in this case, the highest variability was a factor of 2 between those two analysis methods. And that is consistent with what is seen if you take any method and do sequential sampling on a soil vapor point. We actually saved their laboratory some downtime. The first sample, literally the first sample we did of the day, was probably close to pure product. It ended up being over 100,000 micrograms per meter cubed of fluorinated solvent in an area that was not supposed to. It was supposed to be a background sample we were taking. There must have been a sand lens or something like that, or there had been someone had dumped TCP at some point at this site. But regardless, our instrument, it saturated our instrument. We did a clear down run, we did another run. Our data then agreed essentially perfectly with the laboratory data. And it's one of the scenarios where if they had run that on the GCMS in the laboratory, they would then have to spend a day cleaning to get down again to the detection. Our instrument has an R10⁴ carryover sample to sample, which I would suggest is critical, particularly in mobile or high dynamic range, high dynamic scenario sampling is a critical parameter to ask about. So if you take a hot measurement, are you going to be back down to your instrument baselines soon? And so understanding that number, if we get a part per million and you want to go down to a part per trillion, you have to run a cleaning cycle because we understand you're going to have a part 10⁴ carryover in your inlet system. So understanding that is critical if you want to be able to do high dynamic range sensing with any tool. And to give you a sense for what is the data that we present, how does this get to the user, what can the user do, what can the user understand? This is data showing. So this is the auto-generated plot, which is available in the as a KNL file generated in real time to show what are the concentrations. And this is a refinery. This is actually alkanes. This is not. We didn't have significant aromatic detections in this. This is the rapid scan data, but there's a terminal over here, and there were significant alkane concentrations associated with that terminal. And so you could very easily see pull out of this data. I'll show later what we do with the back trajectory and triangulation. But then our user interface is centered around delivering the information that provides high confidence in the data. So we're showing the real spectral data here. We show you a history of the results here. And if you click on any of the compounds, it will show you the quality of the spectral match. But again, the goal is not to have this. This is to provide, in post-processing, someone looking, yes, this has all the confidence we have. We have internal flag, we have internal data, we have internal QA/QC, which will flag any anomalous results should they occur. This is give you a sense of what our analyzers actually look like. These are two AROMA analyzers which are currently in Houston. They're not tiny, but they are very much designed for field operations, for mobile operations, continuously sampling while driving, for example. And so, our recommended setup is you get yourself a lithium-ion battery, and then any vehicle you want is now your mobile. So to give you a sense of what this looks like, in January we were deployed with CDPHE and a Camel. It took us 30 minutes to go from this fixed site installation and have it in a rented minivan doing mobile operations. And that day we were able to go around and we were able to hit different sites that CDPHE was interested in. We did our sanity check on a landfill, pulling up the methane signature, of course. There was a drilling site. We had a very clear downwind alkane signature showing up. And again, in this case, you could look at your different alkanes. We had an alkane signal. There was no dying signal, for example, in that. Again, this is the rapid scan data. And then you go by the refinery and you have the very significant alkane signature near the terminal. It can be put into a vehicle as small as a Nissan Leaf. So this is what Houston is running them in. They're just in the back of the vehicle with a battery mounted. So again, our goal is to be able to get you that laboratory quality data anywhere easy. Again, this is CDPHE, a long-term data. This is kind of a fun data set. So sort of our high resolution data is here. You can see there are a bunch of gaps in here. So we were deployed with CDPHE when it was the freeze that froze Texas. But it also was so cold in Colorado that they lost power, and then it was too cold for any of the backup generators to start. And so there are a number of gaps in here where there was just total power loss. The nice thing about our analyzer, we shipped it. It's in a little crate. You kind of see it tucked in here. We just shipped that crate FedEx. It was calibrated within 8% of their standard when we pulled that out of the box and turned it right on their end. Which of course, I'm thrilled. That's perfect agreement for me because I never get two standards that are within 8%. I buy them from the same vendor. Came right back up after these significant events where the analyzer was plunged down to very cold temperatures. Outside of the sort of spec temperature operating range, it was probably down at -5 to -10 inside of that shelter, and without having to go through any kind of recalibration setter, the instrument was back online. We did some work with San Antonio, looking at what were different types of sources. So it's very easy to cover a large enough area with these tools. So you want to understand what the background concentrations for that ethylene oxide. You can look at different types of regions. Are you seeing elevated concentrations from biogenic sources, from different types of industrial activity, et cetera? And I will add that the tool itself is designed as a central node. So it has built-in GPS. It does GPS logging. We've already built in support for both RM Young and Gill anemometers. So if you just get a custom plug from us, you can plug it into the back of the analyzer, intake that wind data in real time. And we support expansion of the different types of analyzers to have our instrument provide to be a hub for online data collection, data processing, and data synthesis. And I guess in kind of to wrap up a little bit. So you mentioned there are two modes of operation: there's the rapid scan and there's the analysis mode. What does this data look like in practice? So actually, in this specific example, we had two analyzers with us. One was running rapid scan the other time, and the other was running in analysis mode for collecting the data. And so when we were looking at the data, we saw there's a very clear methane signature. So in this case, we're showing methane trace as the high data rate trace. And when we look back at what the aligned data was, so this is how we were sampling continuously over this virtual fence line right here. We also had a significantly elevated benzene, which is red here, and then toluene, which is shown here in blue. We had significantly elevated concentrations of those other co-contaminants, which then you look back at the map, and there's a whole bunch of well pads sitting right here adjacent to the highway. So you get clear signatures. In the different modes of operation, you have both methane. You also have your VTEX. Other types of work, again, for sort of critical use cases, we were deployed in the city of Houston after the ITC fire, which was it was a significant event. Concentrations as high as 500 parts per billion of benzene were measured downwind. This one was actually this was really kind of shocking. At some point, we measured Lake Houston, which is about 12.5 miles downwind, and the concentrations were still 10 to 15 times background. You could drive into the flume and see very high concentrations, very far down. And this is a scenario when it looked really bad initially. The on-the-ground concentrations weren't necessarily as high because you had this nice uplift, which is getting everything kind of out of the ground region and only contacting that wind. Unfortunately, without that thermal uplift, you then saw elevated concentrations after that time. Other kind of work and what do you do with this data? So, in that previous case, we were tasked with sort of setting ourselves in a downwind scenario to understand what the concentrations or what the impacts might be. After Hurricane Harvey, we were working with the Environmental Defense Fund of the city to do a broad area measurement in the Houston area. A number of plumes were identified. The highest one that the city was interested in initially was this Manchester plume, so we did significant evaluation of the sources in the area adjacent to the Manchester refinery, and we ran maximum likely back trajectory calculations to identify the source area. And if go on Google Maps a couple of days later, you can see this is the tank that had the flooding issue. This was an astonishing rain event, and there were issues where the tank roofs sank because they had so much water on top of them. So I believe that was the scenario that happened here. But this was chaos on the ground, right? I mean, there were millions of gallons of product that were lost as a result of this, and without being able to collect data and understand, well, today, right? Who do I have to worry about? Where is there a potential ongoing problem? There were tons of releases. This wasn't thought to be the biggest one. This ended up being the highest concentration. But with these kind of tools, you can do triage. You can identify, yes, there were a bunch of leaks, but the concentrations are not problematic. This one ultimately, we were sort of at 100 parts per billion kind of concentration, but that was the highest concentration. So it was useful to help identify how do you focus the city resources so they have a mobile laboratory that after the sort of triage, able to put their mammal on site to do continuous monitoring in this community, for example. And one of the useful things is that without actually a huge amount of work, you can do interesting source fingerprinting. So we just ran a trivial fingerprint benzene toluene ratio, and we had very tight clustering across a variety of different plumes that we're seeing. This was an early analyzer, so they're really just going to detect. We do many more compounds now in these analyzers. But for example, at one of the plumes, it looked like a single plume, but on one side it had this source concentration. As you drove across, it pulled out over to this benzene toluene ratio, which it then became clear that there were actually two plumes which were spatially overlapped. You could very easily tease them apart using something as sort of simplistic as a benzene toluene ratio. So tools are out, being used by a number of different organizations. We're a little bit early, but I'm happy to open up and answer any questions at this time that the audience might have.
How much would he say back?
I mean, the base price for the analyzer is 120.
Okay.
And there are different variants. I mean, well, actually, so the base price is 100. There are different feature sets.
Specifically.
Yeah, it depends on exactly what. There are a couple of variants in terms of like, does it have the rapid scan mode? Does it? Right. So there are, but that's kind of the base, the price ballpark.
So the detection limit for the ETO on the lab scan mode, we're doing the separation with the part per trillion, but the detection limit when you're doing the rapid scan mode for ETO is
part per billion.
Part per, like 50 part per billion? Or
no, one.
Like single digit part per billion?
Single part, yeah, one or better.
Okay. Yeah. And then I have a bunch of questions, so if y'all have something else. Jump in. So like all the overlapping features, are you guys experimenting or doing the cavity breakdown at like millitorr pressures, or try to separate some of those, or are you just what pressures are you operating?
I mean, it depends on which mode we're in, but I mean, we're not operating in millitorr pressures. I mean, you don't tend to get much advantage below 100 torr or so. So I mean, when we're in direct CRDS mode, we do pressure controlled CRDS. We do reduce pressure CRDS, and there's, just to give a little context. So those narrow features we saw before, right? They actually are broadened out by just the molecules running into each other and the lifetime of collision broadening. And so if you actually reduce your pressure, the peaks themselves stay at almost exactly the same height, but the valleys get deeper and deeper. And so ethylene oxide is not strongly affected by pressure changes. the advantage is that, it's sitting in a valley, water and methane valleys, and those valleys come down significantly as you reduce the pressure.
Which also have less molecules, so they're not like.
So right. So there's a trade-off between what is your absolute molecular sensitivity and what is your ability to do background rejection. And so there's an optimization that's done, on what pressure do you want to set in terms of the overall instrument performance.
And what frequency are you gathering for the cavity right now? At place at 40,000 per second, or?
No, it's in the. I mean, honestly, it varies based on what the baseline decay rate is of your cavity, and so again, but this is like So you buy mirrors and you spec a mirror performance at the center of your wavelength range. We're covering a very broad wavelength range. So we're covering more than 100 nanometers. So you have significant variability inside of that wavelength range. And so, for example, optimally, you can adjust your CRDS rate to match. So, we run we're doing cavity lock CRDS. We have very high data rates. We have essentially 100% cavity fill fraction, and we're able to do that. We can adjust the ring down rate to optimally, to get an optimal bit depth. Essentially, you want to measure for about 5 times your decay envelope to get optimal signal to noise. So we can dynamically vary if we need to that decay, that measurement rate, so that we have the cavity fill fraction, and then we do get the best signal to noise out of the CRDS system.
What was that again? I mean, you say I thought I heard you say what it was. Normal one.
I mean, it's typically, again, we're typically looking at a 400,000 finesse cavity. It's 10 centimeters or so. But we're typically looking at 1,000 to several thousand, up to 10,000 measurements per second. Again, it's depending. It depends on, which specific analyzer we're talking about. For our analyzers, for our oil field analyzers, we have a different, it's a different set of parameters than it is for our VOC analyzer, for example.
And I guess it was slide 17, I think, the ethylene oxide one, it was very diurnal that you were.
Yes.
What's your theory on that? If you're saying it just, if you're thinking it was just background, what's causing it?
Oh, so the place we're located, we have very strong diurnal variation in wind pattern. So we're right by SFO, and so if you've ever driven like up 280, it's like the most beautiful drive. And you see in the afternoon, for example, you have thermal uplift in the valley, it pulls fog over, and so you can see, for example, you have a strong air exchange. So we're right by SFO, so it's an even stronger effect. So we have very strong diurnal variations in the wind in those areas. Beyond that, honestly, I have no idea. I don't know where this is coming from. Like it's really, this is kind of early days, right? And so there is clearly a strong diurnal variation. I know we also have diurnal variations in everything we see because we're getting pretty clean air off of the Pacific Ocean every day where we're located right there.
I heard you say you had, again, I might go, how to find out, but you said you were very encouraged about the 8% agreement between your standard and Denver standard, I guess. Have you had or experienced problems in getting ethylene oxide standards that are pretty?
No, this is not. That was not ethylene oxide. That was actually I don't know how to get ethylene oxide standards. I talked to the people at EPA. They don't know how to get it. So I will say all of these numbers. There's whatever the uncertainty is in the analytical standard we were using. It was I believe it was it was a gravimetric standard we were using. I'm assuming those concentrations are that. Over time, we don't really understand, what the dynamics are. I'm assuming that the concentration is lower in that Cal standard, if it's anything, right? Which would then actually shift our sensitivities higher. So there are some real just mechanistic challenges with dawn of the supply chain to get good analytical standards. It seems like nobody knows how to do that. EPA doesn't know how to do it. They're still working on the methodologies. They're still working on certifying vendors. So yeah, that's a caveat behind all of this. But yeah, I can say our general experience is that we buy Cal standards and we run one Cal standard, we run the next Cal standard, and they're varied by, they say they're 5% certified and they're off by 10 to 15%. It's not uncommon in our experience. Now, again, I don't want to name the vendors, et cetera, but it's a challenge that we've had. So that's why I sort of say we get 8% agreement. As far as I'm concerned, that's great agreement. We could have called that out if we wanted to at the beginning. The Cal is stable over the lifetime of the mesh chain.
For the mobile monitoring events, what speed are you traveling at when you're capturing that spatial information?
It depends. So typically we're, unless it's sort of more of an urgent response kind of scenario, I mean, we're going to go whatever highway speed is at that time. Because I don't want my guys, I don't want to, velocity differential between my guys out in the field and like, unless we really need to. So it's typically at highway speeds. And, there are limitations associated with that. When you're doing a mobile measurement campaign, we will typically, depending on the overall outcome, like what the data objective is, right? For that study, we'll either do very fast sampling, so we'll try to essentially grab point sources, or if it's looking more at broad area averages, we'll then explicitly derate the sampling. So we'll take longer samples so we get higher coverage. We then are doing spatial averaging, so we become less sensitive to point sources. So again, it depends a little bit on what the study objectives are, how you select your measurement methodology. But one of the things we've really tried to do is make the tool really easy. So if you want to change, you pick your sample volume and you pick your measurement duration independently. And so it's very easy to dial in instrumentation parameters to achieve your study objectives. And I guess the other thing, we don't have a slide on this, data quality is critical, and QASPs are typically operated. It depends on what the scenario is. So most mobile measurements, include daily bracketing, calibration verifications. One of the nice things about the tool is that we don't have to adjust the calibration of the tool. It's very stable, very robust long term. But of course, any data quality package, right? You want to make sure is your sampling system working, is everything working, so you actually have that full data quality package. But again, that's totally dependent on who you're working with, right? What the requirements are, what the data use is, et cetera. Great. Thank you very much. Appreciate your time. Thank you.